I apologize for the buzzing that happens when I'm connected via cable, but all right, heat of solution is defined as the energy absorbed or released when we dissociate 1 mole of an ionic compound in water. You wrote these kind of reactions in honors, but we're definitely going to go a little bit deeper here. So let's say, for example, I am dissociating calcium chloride. It's a solid. When I put it into water, I end up with 1 calcium ion, which we indicate as aqueous or dissolved in water, and 2 chlorine ions. I don't get chlorine gas, I get dissociated ions. I can get the heat of reaction for this using this table, but it's important that I know more about what's going on at the molecular level here. We have bonds being broken and bonds being made. The bonds that are being broken are between ions. So between calcium ions and chlorine ions. The bonds that are being formed are between ions and water. The positive calcium ion will attach to the negative side of water, and the negative chlorine ion will attach to the positive side of water. Bonds being broken requires an energy input. So this step is endothermic. Bonds forming releases energy, and this step is exothermic. Whether the dissociation overall is endothermic or exothermic depends on the relative magnitude of those two steps. Is more energy required to break than we get back from new bonds forming? Then that'll be an endothermic dissolution. Some definitions you need to know. Lattice energy. Lattice energy is a way of measuring the strength of an ionic bond. A higher lattice energy, stronger ionic bond. The definition of it is the energy required to break 1 mole of an ionic compound into its gaseous ions. Gaseous ions aren't something you normally see, but it means we're going simply from, we're going simply from something like solid sodium chloride, and we're just separating the ions from each other. If we're separating them from each other by great distances, we say they are gaseous. In other words, this is not accounting for the attachment to water. This is just breaking a bond, no new bond forming. So this step is endo, or it's going to have a positive delta H always. This would be step 1 of the process. Step 2 of the process is now my gaseous ions being attached to water molecules, and my sodium gaseous ion becomes a sodium aqueous ion. And my chlorine gaseous ion attaches to a water molecule and becomes an aqueous ion. This is the enthalpy or heat of hydration. And that's the energy released when the ions attach to water. This step is always exo or a negative delta H. So there's some things when we dissolve in water overall are endothermic and some are exothermic, once again, because it depends on the relative magnitude of these two steps. Let's take a look at some samples where we find delta H reaction for dissolving reactions. So I'm going to write the dissolution reaction. I have ammonium nitrate, which is breaking into ammonium and nitrate. You should break an ionic compound into the ions that made it up. But also the back side of this table has positive ions and negative ions. If I'm going to ask you to find the heat of reaction for this, you're going to have to use these values. So you can look here to find what's relevant. To get delta H reaction, I have 2 products and 1 reactant. For the ions, I'm using the back of the table. Ammonium is negative 132.8. Nitrate is negative 206.6. And then from the front, ammonium nitrate is negative 365.1. Negative 132.8 minus 206.6 plus 365.1 gives me a positive 25.7 kilojoules per mole, or in AP fashion, kilojoules per mole reaction. Is this reaction endo or exothermic? We can tell from that. It's endothermic. So when I dissolve it in water, it should make the water colder. Calcium chloride, however, you can probably tell that this one's going to be exothermic if I'm using it as an example also. Breaks into those ions. And when I'm doing the heat of reaction, which in this case is equal to the heat of solution, because it's a dissolving reaction, calcium ion, negative 543. I have 2 chlorine ions. Each one is negative 167.4. Calcium chloride's on the front of the table, negative 795. So this is going to be negative 543 plus 2 times negative 167.4 minus a negative or plus 795, negative 82.8 kilojoules per mole reaction. And this reaction is therefore exothermic. If you can write heat of reaction, if you can find the heat of reaction, you can then use these problems in just as you would other ones, where you can then do a ratio afterward if necessary. And that should be all we need.